Hello students, good afternoon. Welcome to the second part of the chapter coordination compounds. Okay, so in this part we will discuss cationic, anionic and neutral complexes. So coordination compounds are complexes may be of following types. Number 1, cationic complexes means the complexes in which the complex ion carry a net positive charge are called cationic complexes. For example, FeH2O whole 6 after the ionization it will give FeH2 का whole 6 3 plus. So in this complex compound, the complex compound carry positive charge, net positive charge of 3 plus ion. So these type of complex compounds are known as cationic complex compounds. Okay, next anionic complexes. So in this type of complexes the complex compound will carry negative charge. For example, K4 FeCN6 after ionization it will gives FeCN6 4 minus. So here you can see that at the complex compound there is a negative charge will be present. Okay, now neutral complexes, the complexes which carry no net charge are called neutral complexes. For example, NiCO whole 4 PtNH3 Cl2 etc. So these are the neutral complexes. Now coordination number. So the maximum number of ligands which can be coordinated to a central atom or ion is known as the coordination number. For example, in this complex K4FeCN whole 6 there are total 6 number of ligands are attached to the central atom ion. So the coordination number of this complex will be 6. Okay, so number will be 6. So according to the number of ligands attached to the central atom ion, the number of ligand will be the same. Okay, now charge number or complex ion. So what is the charge number? So the charge present on the complex compound in positive or negative value basically known as the charge on the complex ion. For example, in this complex ion there are 4 minus charge is present, so that is the so it will known as charge on the complex ion. Now oxidation number or oxidation state of central atom. So how you will calculate the oxidation number on the central atom? For example, in this complex compound iron Fe is a central atom. So at this Fe what will be the oxidation state, means what will be the charge present on this, how will you calculate? So for example, oxidation number of copper in CuNH3 whole 4 SO4. So we have to calculate the oxidation number of copper. So for copper we will suppose X plus 4 ammonia is a neutral atom. So there is a number of ammonia is 4. So 4 into, because it is a neutral ligand, so it will not give any charge. So 4 into 0 and minus 2, and this minus 2 will come from the ionization of this complex ion and equals to 0. So after the calculation the value of X will come plus 2, means the oxidation state of copper in this complex will be plus 2. So on this way you can calculate the oxidation number of any of the central atom of the complex ions. Okay, now so there are other examples are given here, you can see. Now homoleptic and heteroleptic complexes. So the complexes in which the central metal atom or ion is linked only one kind of donor atoms are known as homoleptic complexes. For example, FeCN whole 6. So here only cyanide ligands are present, no other type of ligands are present, so it will known as homoleptic complexes. Okay, other example CONH3 whole 6 3 plus, so it is also a homoleptic complexes. But in heteroleptic complexes the donor atom of the central atom ion will be different. For example, CONH3 whole 4 and Cl2. So in this complex there are ammonia and chlorine will be present, so both the ligands are different. So this type of ligands will called as heteroleptic type of complex compounds. Okay, so these are the some terms which are used in coordination compounds. Now classification of ligands. So classification on the basis of charge. So firstly, neutral ligands. Such ligands possesses no electrical charge present on them, and they are usually molecular species having one or more lone pair of electrons. For example, water carry 2 lone pair of electron, ammonia carry 1 lone pair of electron, carbonyl no lone pair of electron, nitrosyl NOCl and pyridine C5H5N. These are basically known as neutral ligands. Anionic ligands. Such ligands carry negative charge on them and they anionic species containing one or more pair of electrons. For example, F for F ligands, the suffix fluorido will be used. Fluorido, Cl chlorido, Br bromido, iodido, Cn cyanido, OH hydroxo, CH3 COO minus acetato. Okay, so these are abbreviations of the ligands during the nomenclature of IUPAC. Now come to the cationic ligands. Such ligands carry positive charge and occurs very rarely in complex compounds. For example, NO plus nitrosonium and NH2 NH3 hydrogenium means for ligand which carry plus charge, the suffix em will be added at the last of the name. Okay, for example, NO plus is basically known as nitroso. So after nitrosyl, NO is basically known as the nitrosyl. So if you will add em, so it will called as nitrosonium. Okay, nitrosylium. Okay, now classification on the basis of number of donor atom. So if there are only one atom is present which donate lone pair of electron, so it is known as the unidentate ligands. The ligand which possesses only one donor atom and can form only one coordinate bond to the central atom are known as unidentate ligands or monodentate ligands. For example, there are many ligands which are monodentate. For example, ligands ido, cyano, hydroxido, nitrito, acetato, thiocyanito, isothiocyanate and amido. So these are some examples which are monodentate ligands. Now bidentate or didentate ligands, the ligands which possesses two donor atoms and can form two coordinate bond with central atom ion are known as didentate ligands. Okay, examples are oxalato, COO minus CO minus oxalato, glycino, NH2CH2CO minus. There are nitrogen will can donate electron and oxygen will also donate electron. And after that ethane 1,2-diamine. So here there are two nitrogens at which there are two pair of lone pair of electrons present, so they can be donated both the pairs, so it will be bidentate type of ligand. So these are some examples of didentate or bidentate type of ligands. Now come to the tridentate ligands. Means those type of compounds in which there are three atoms present which can donate the electrons are known as the tridentate ligands. For example, NH2 CH2 CH2 NH CH2 CH2 NH2. So here three nitrogen can donate the lone pair of electrons, so it is an example of tridentate ligands. Okay, now tetradentate, in which the central atom, four atoms which can donate the lone pair of electrons are known as the tetradentate ligand. It is an example of tetradentate. Now after that penta, in penta 5 atom can donate the electrons, and after that will come hexadentate ligand in which 6 atoms can donate the lone pair of electron to the central atom ion. 2 nitrogen and 4 oxygens can donate the lone pair electron to the central atom and form a complex compound, so it is a type of an hexadentate ligand. Okay, so it was the classification of ligands. Now come to the Werner's coordination theory of complex. So what is the Werner's coordination theory? So the scientist Werner's he gives some points according to the complex compound. So postulates of Werner coordination theory, the main postulates are: number one, the central atom oblique ion present in a complex compound exhibit two types of valency, that is known as the primary valency and secondary valency. So what is the primary valency? This type of valency is ionizable and corresponding to the oxidation state of the central metal ion, and it is always satisfied by the negative ions. Okay, for example, you can see the complex compound FeCN whole 6 Cl3. So the term which will written outside this square bracket will known as the primary valency, and it will be ionizable. Secondary valency, in which if the complex compound in which the ligand which is directly attached to the central atom, and the number of this ligand will basically known as the secondary valency. Okay, so you can see this on this structure in which the ammonia contains the primary secondary valency, and the chlorine which are attached to the dotted bond will known as the primary valency. So this bond can be break and chlorine can be easily ionized. So it will known as the primary and secondary valency. Okay. Now the central atom, the central metal atom or ion has the tendency to satisfy all the primary and secondary valencies. In order to meet the requirement, the central metal atom or ion may attach one or more negative ion through both the primary and secondary vacancies. Okay, the secondary vacancies are directional and they point the definite direction in space. Means according to the secondary valency, for example, this NH3, NH3, NH3. So, if the secondary valency will attach to the central atom, then it will form a geometry. So, we can say that secondary valency is directional. Okay. Now, on the basis of Bernard's coordination theory, there are some examples are given. Okay. We will discuss in next video. Okay. Thank you. Have a nice